NASA's newest space observatory allows researchers to see further into the cosmos than ever before.
The James Webb Space Telescope, with its unmatched infrared sensitivity and powerful imaging capabilities, has once again pushed the boundaries of what humanity knows about the cosmos. In one of its most recent and puzzling observations, the telescope has detected a series of galaxies behaving in ways that challenge our current understanding of physics and cosmic evolution. These galaxies, spotted in a distant part of the universe nearly 13 billion light-years away, are not only larger and more developed than expected for their time period, they also appear to contain massive mature stars that should not yet exist at such an early stage of the universe's life. Before we start, smash the like and subscribe buttons for more updates. This strange discovery centers on the observation of unexpectedly massive galaxies that formed less than 500 million years after the Big Bang. According to prevailing cosmological models, the early universe should have been a chaotic soup of elementary particles, with only the smallest proto-galaxies just beginning to take shape. Yet the Webb Telescope, peering far into the past through the haze of cosmic history, found behemoth galactic structures with complex features, spiraling arms, dense star clusters, and immense quantities of stellar mass. The presence of these mature features at such a nascent epoch contradicts nearly everything astrophysicists had previously theorized about how matter coalesced after the birth of the universe. The implications of this discovery are staggering. For decades, astronomers have operated under the assumption that the formation of large-scale cosmic structures followed a gradual, step-by-step process governed by dark matter scaffolding and the slow gravitational pull of accumulating baryonic matter. The appearance of these early massive galaxies throws that notion into question. It suggests that either galaxy formation is far more efficient than once believed, or some unknown mechanism, perhaps involving exotic physics, accelerated the development of these colossal systems. What makes this even more perplexing is the composition of the stars found within these galaxies. Observations from Webb's near-infrared spectrograph NIRSpec and mid-infrared instrument MIRI indicate the presence of heavy elements, metals like oxygen, carbon, and even iron, that should not have existed in significant quantities during this epoch. These elements are generally produced in the cores of aging stars and distributed through the cosmos via supernova explosions. The detection of such metals implies that at least one generation of stars had already lived and died, which would mean that star formation began far earlier than anyone had anticipated. This opens up questions about the rate at which the universe cooled and condensed into stars and galaxies after the Big Bang. It may indicate that the so-called dark ages of the universe, an era before the first stars ignited, were much shorter than previously estimated. If stars were forming and dying within just a few 100 million years, the entire timeline of cosmic evolution may need to be rewritten. Theoretical models that once comfortably explained the appearance of galaxies, black holes, and cosmic structure over billions of years may now require a radical overhaul to account for this rapid early development. Even more astonishing is the discovery of highly energetic activity in the cores of some of these galaxies, hinting at the presence of supermassive black holes. Supermassive black holes, millions to billions of times the mass of the Sun, are believed to take vast amounts of time to form, either by accreting matter slowly or merging with other black holes. Yet the Webb Telescope has found evidence that such giants were already lurking in the hearts of these ancient galaxies. These findings defy the standard models, which cannot easily account for how black holes of such size could arise in such a short time span after the universe's birth. Some of the galaxies observed also exhibit unusual infrared signatures that suggest either obscured starburst activity or novel processes entirely. In several cases, their infrared luminosity far exceeds what should be possible given their age and size. This could point to hyper-efficient star formation, exotic matter interactions, or something even more enigmatic, phenomena that current physics has not yet predicted. The energy outputs from these galaxies hint at violent, transformative processes underway: galactic winds tearing through interstellar space, stars forming in dense molecular clouds at unprecedented rates, and perhaps the presence of dark matter behaving in unexpected ways. Another dimension of the mystery lies in the spatial distribution and clustering of these early galaxies. They appear to be forming in denser groups than models of the early universe allow for. This clumping might mean that cosmic structure began forming earlier and more rapidly, or that the seeds of structure, possibly tied to primordial quantum fluctuations, were stronger and more influential than previously realized. Such a realization could dramatically impact our understanding of inflation theory, the concept that the universe underwent a brief but rapid expansion right after the Big Bang. If structure arose sooner or more effectively, it might suggest a fundamental flaw in how inflation is currently modeled. These strange findings are not isolated to a single patch of sky. Multiple surveys conducted using Webb's deep field imaging techniques, where the telescope stares at a single region of space for hundreds of hours, have revealed similar anomalies in widely separated areas of the cosmos. This suggests that the phenomenon is not a local aberration, but a widespread feature of the early universe. If so, it could represent a fundamental shift in how we interpret the earliest chapters of cosmic history. One of the more speculative yet compelling explanations gaining traction involves the idea of modified gravity or early dark energy. Some theorists propose that the fundamental forces governing the universe may have behaved differently in its earliest stages. Perhaps gravity operated more strongly, enabling faster collapse of gas clouds into stars and galaxies. Or maybe a variant of dark energy, normally associated with the accelerating expansion of the universe, played a more active role during the early epochs, shaping matter in ways that standard dark energy models do not predict. If any of these speculative ideas prove true, they could open the door to entirely new physics, perhaps even reconciling quantum mechanics and general relativity under a new framework. The possibility of unknown particles or forces also enters the discussion. The early universe may have harbored conditions conducive to interactions with particles not yet discovered, components of the cosmos that influence structure formation in ways current experiments have failed to detect. These could include dark photons, axions, or other exotic forms of matter that alter the way energy and gravity distributed themselves across space-time. If Webb's data continues to support this line of inquiry, the telescope could play a key role not just in astronomy, but in the future of particle physics. Another intriguing interpretation revolves around the potential for early universes or cosmic cycles. Some speculative cosmological models suggest that the Big Bang was not the absolute beginning of everything, but rather the latest phase in a continuous cycle of expansion and contraction. Under this framework, certain imprints or structures could carry over between cycles, seeding the new universe with matter and organization from a previous one. These ideas remain highly controversial, but the Webb Telescope's discoveries have given them a surprising relevance in current scientific debates. On a more grounded level, some researchers are revisiting the assumptions baked into our interpretation of telescope data. The redshift distance relationship, for example, is used to estimate how far away and how old the observed galaxies are. If redshift behaves differently under certain extreme conditions, something not entirely implausible, then perhaps these galaxies are not quite as old or as distant as they seem. Even slight adjustments to redshift calibration could have major effects on our understanding of early universe observations. Yet so far, the spectroscopic data gathered by Webb remains robust and consistent, reinforcing the notion that the telescope truly is looking back in time to a previously unseen corner of the cosmos. More practically, these discoveries compel a re-examination of the simulations and models astrophysicists rely on to predict galaxy formation. Many of these simulations, such as Illustris or Eagle, are based on known physical laws and assumptions about how matter behaves under the influence of gravity and radiation, yet none predicted the early emergence of massive structured galaxies to the extent now observed. As new data streams in, theorists are scrambling to modify these models or build entirely new ones, incorporating fresh parameters and perhaps even embracing new physics to account for what Webb has revealed. The deeper Webb peers into the universe, the more it is unveiling a cosmos full of complexity, contradiction, and wonder. These discoveries, far from being mere anomalies, could represent a new frontier in our understanding of how the universe truly works. For every answer the telescope provides, it seems to raise 10 new questions. Its instruments, designed to read the faintest whispers of light from the first billion years of existence, are bringing us face to face with a universe that is not only stranger than we imagined, but perhaps stranger than we can imagine. This is not simply a matter of fine-tuning models or correcting data errors. It may be that the Webb telescope has begun to expose cracks in the foundation of cosmology itself, prompting a deep, and possibly revolutionary reassessment of our place in the cosmic order. The galaxies, it is revealed, speak of a time when the universe was young but somehow already wise, full of structures and energies that defy the constraints of current understanding. In doing so, the telescope has not only advanced science but reignited the very spirit of discovery that drives it. This strange happening in the universe, a glimpse of ancient impossible galaxies blooming in the early darkness, reminds us that the cosmos is still vast, untamed, and full of secrets. As more time is dedicated to studying these phenomena, and as more data pours in from the James Webb Telescope and future observatories, humanity stands on the cusp of potentially rewriting the very narrative of cosmic creation. And somewhere out there, in that shimmering veil of stars beyond time, the answers are waiting. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on what JWST found? What do you expect it is? We want to hear from you. Thank you for watching, and see you next time.